Have you ever heard a scary noise in the middle of the night, but it was too dark to see? Or tried to navigate your house during a blackout? We take for granted our ability to flip a switch and, like magic, we have light. But is it really magic? Today, we're going to show you how a light bulb works. Light bulbs are actually just fairly simple little machines that convert electrical energy into light energy. To understand how a light bulb works, we first have to understand what light actually is. Light is a type of electromagnetic radiation. That means it's energy that's being emitted from an atom in the form of a photon. Photons move around in waves, and the amount of energy it has determines what form of light it is. Radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, or gamma rays. Some waves, like radio and TV waves, are long and less energetic, and some, like gamma rays, are short and excited. Think of two balls moving at you at the same rate. They cover the same distance, but the blue ball is moving around much more than the red ball. It has more energy and a much shorter wavelength than the red ball. Not all photons are in the visible light spectrum. Those with very short wavelengths and a lot of energy are gamma rays or X-rays, and those with long wavelengths, meaning less energy, are radio waves. But if they're moving at just the right wavelength, a photon can be seen as visible light. So where do these photons come from? Let's take a look at an atom. An atom has positively charged protons and neutral neutrons in the nucleus. A cloud of negatively charged electrons orbits the nucleus. These electrons move around in orbital shells, and generally speaking, the higher shells have more energy per electron than the lower ones. When an electron gets excited, it might jump up to a higher orbital shell, so it has a little bit more energy. You may have heard the phrase conservation of energy. Energy can't be created or destroyed. So when an electron calms down and returns to the lower shell, that energy has to go somewhere. It's released as a photon. The wavelength of that new photon depends on how much energy that electron had. But where do we get the energy to excite the electrons enough to jump to a higher orbital level? They'll do so if the atom they're attached to starts moving around. In other words, if the atom gets enough energy and heats up. Heat is just the energy of atoms moving around a lot. And to get an atom to move around, you can crash some spare electrons into it. When you have a lot of atoms, like you would in a piece of metal, you'd need a stream of electrons to crash into them to make all those orbital jumps. And guess what a flowing stream of electrons is called? Electricity. Let's go back to our light bulb. To make light, you need a filament made of some material that will allow for the flow of electrons. If the material you use has too much resistance, like wood, the electrons can't get through to hit enough atoms. But metal is a good material because it's a good conductor of electricity. It has a lot of electrons that move around freely. So most filaments are made out of metal. It's held up on a glass mount and connected to a power source so that electricity can flow into and out of the bulb. The filament is the key part of the bulb. It's the thing that produces the light that we want. Remember, the amount of energy that a photon has will determine how excited it is. In other words, what its wavelength is. We can't see too high or too low wavelength photons. Our eyes can only see a small band of the right wavelength photons. Now, when you begin to heat most metals, they release their photons in the infrared spectrum of light, so we can't detect it with our eyes. As the metal gets hotter and becomes more energized, the photons in the visible spectrum of light are added to the mix, starting with red and continuing until all the colors are added and we see it as white. This is why white hot metal is at the highest temperature. To get that color, you need a lot of photons emitted. Luckily, there are a lot of atoms in a light bulb filament, about 10 sextillion, and they're all releasing photons. These photons are being emitted at all different wavelengths, some at long wavelengths, like radio waves, and some at short wavelengths, like UV rays, and they're all continually being absorbed and re-emitted. All these photons combined is called black body radiation. When you combine all the wavelengths that make up the visible spectrum, we see it as white light. So even though our filament is emitting a lot of photons that we can't see, we just need to have enough of them moving in the visible part of the spectrum for our light bulb to work. And it turns out the wavelength of photons that an atom emits basically depends on temperature. There's a fancy formula that shows this using Planck's constant, Boltzmann's constant, the speed of light, frequency, temperature, but don't worry, just know that if we can heat that metal high enough, we'd have enough electrons crashing into the atoms of the metal, and those photons start moving at a shorter wavelength until they reach the visible light spectrum. In most incandescent light bulbs, the filament reaches around 5,000 degrees Fahrenheit. Now remember, what we're essentially trying to do is convert electrical energy into light energy by first changing electrical energy into thermal energy, which we'll use to heat our metal. Heat will excite our electrons and make them emit energy as photons, and we want to have as many of these photons as we can be in the visible light spectrum. During each step, we lose some energy. Not all electrons will cause an atom to move, not all moving atoms will have an electron jump orbital shells, and not all photons emitted will be in the visible light spectrum. So, incandescent light bulbs aren't very efficient at making light, and a lot of the energy we put in isn't actually turned into something we see. That's why light bulbs get really hot. One thing to note, a lot of photons still don't reach the visible light spectrum even after adding all that heat. If we could heat the metal up to 8,000 or 9,000 degrees Fahrenheit, we'd get a lot more visible light. But that's not very practical, since that's about the temperature of the sun. Under the right conditions, really hot metal will actually catch on fire. In other words, it will react with the oxygen in the air. But if we can put it in a vacuum and protect it, we can prevent combustion. That's why light bulbs are housed in a glass bulb, usually filled with an inert gas like argon. Another problem is that most metals melt at such high temperatures. It turns out that the metal tungsten has an abnormally high melting temperature, and that's why most light bulb filaments are made out of tungsten. So why are light bulb filaments so thin? That has to do with electricity and the flow of electrons. We want to make sure enough electrons hit our tungsten atoms to get them excited. If our piece of tungsten was too thick, it would be too easy for our electrons to get through. We want enough resistance in the path of the electron current. Here's another way to think about it. Think of yourself as an electron and the tungsten as a hallway of people that you have to run across. If the hall was big and expansive, it would be easy to cross without bumping into anyone. But if you narrow the hallway, you'd bump into a lot of people, transferring your energy with every contact, jostling the people milling around. That's what's happening with the electron flow going through the tungsten filament. In a light bulb, the filament is about 1/100th of an inch thick. But one really thin glowing wire of tungsten wouldn't be very bright. So to make it brighter, the filament is arranged in a double coil to fit inside that small space. In a typical 60-watt bulb, there's about 6.5 feet of coiled wire. So as the stream of electrons flows through the thin coil of tungsten, it starts heating up, gets excited, and begins to emit photons. When enough of these photons are emitted at the right wavelengths, we see them as visible light. Do you know who invented the light bulb? Well, you may be surprised. The idea of a light bulb actually started way before Thomas Edison. Over 20 people had ideas and working prototypes before him. Sir Humphrey Davy invented the first electric light in 1802, but his battery-operated lamp didn't last long and was too bright for practical use. The first light bulb, made with carbonized paper filaments, was created by Joseph Swan in 1850. But since vacuum pumps at the time weren't very good, they had too short of a lifespan to work well commercially. He actually partnered with Edison to sell electric lamps. Thomas Edison's company, the Edison Electric Light Company, began in 1880 and used carbonized bamboo filaments. His bulbs lasted over 1,000 hours, so he could market it to the general public. Tungsten filaments were first used by Hungarians Hahnemann and Just, then perfected at the General Electric Company by William Coolidge. And filling the bulbs with inert gas was the idea of Irving Langmuir. So Edison didn't invent the light bulb, but he was the most successful at commercializing and marketing it. Tonight, when you turn the lights on, you can thank not just Thomas Edison, but Davy, Swan, and a whole host of others for inventing and perfecting the light bulb. We hope today's lesson was illuminating. Thanks for watching, and we'll see you next time.